Okay, so today's start on gravitation is going to be a little bit of history. Physics history. And you're probably going, geez, history's boring enough. Now you're going to tell me about physics history? It's even worse. Oh, snore. Okay, but in actual fact, this is kind of an interesting story because there's a lot of drama in this story. Okay? So originally, even well-established and well-respected physicists believed that the Earth was at the center of the universe. Okay? That was what everybody believed. And it made sense given the instruments and experiments and things like that and observations of the time. Okay? Even the Greeks, they had the idea that everything moved around the Earth because if you watched the night sky, that's exactly what happened. Everything moved around in the sky. Okay? And it appeared to go around the Earth. Nobody realized that it's because the Earth was actually spinning underneath them, but hey, nobody knew that, right? These were reasonable observations for the time. Now, as people continue to observe and get better equipment and start to actually make note of what the stars in the heavens were doing, even people like the Greeks way back noticed that some of the stars didn't behave like others. Most of the stars stayed put, but a few wandered. In fact, that's what the word planet means, is wanderer. Okay? Some of these stars moved about in the sky, and so they were special, and they were given special names, like the names of the gods, okay, and things like that. So further on, okay, as history kind of progressed, and time passed, and the telescope was invented and stuff like that, people made more and more detailed observations of the motion of objects in the sky. And a small group of scientists started to say, you know what? Maybe the Earth isn't the center of the universe. Or maybe the Earth actually orbits the sun. And that was not a well-accepted idea, at least early on. Okay? But as more and more people continued to make observations, more and more people started to buy into it. Copernicus, okay, started getting people to think about it, and so on. Now, eventually it came to the point where there were the two fairly equally sized groups. People who thought the Earth orbited the sun, and the people who thought the Earth was the center of the universe. And you know what happens when you get two equally sized groups who are vehemently opposed to each other's views? We have no experience with that over the last 2 years at all. Okay? But we know what happens. Okay? So a guy named Tycho Brahe had spent his entire life recording the movements of objects in the sky, notably the planets. And by his entire life, I literally mean that. Like his entire adult life. He basically slept during the day and stayed up at night and made notes and tracked the exact position of objects in the sky. He had volumes of written material and notes on the position of various objects. Tycho Brahe was one of the people who believed that the Earth was at the center of the universe. And most of his observations seemed to support that idea. Problem was, there were some observations that did not. The most important observation was the movement of Mars. Okay? Because of the long time frame for planets like Jupiter and Saturn and the other outer planets, which weren't even really discovered then, okay? Because of how long it takes them to orbit the sun, in a lifetime, for Jupiter, you might see Jupiter go around the Earth, if you lived a very long time, 8 times. Okay, so he didn't get a chance to observe Jupiter's movement very much, but he did notice there's just some slight hesitation in its apparent movement through the sky. Okay, but for the other planets, you can't observe a full orbit, so it's kind of hard to kind of see how that works. Mars is quite close to Earth. Okay. And so as a result, he could observe its passing, or Earth's passing, okay, lots of times. And what he observed was that Mars would move, just like all the other planets, nicely around the Earth, just like it was supposed to, except that at some point in its orbit, it would stop and move backwards, and then turn around and go back again, and then start continuing on in the circle. Now, if you believe the Earth is the center of the universe, that movement is very difficult to explain. why would a planet orbiting the Earth just stop, back up, stop, and go back the other way again? And it just doesn't fit with any of the mechanics of that idea or that concept. So Bray got frustrated, and he finally said, you know what, maybe I just don't understand the math of this well enough. So he hired a mathematician. The work was tough for mathematicians then. There wasn't a lot of work for mathematicians. Okay, so he wanted to hire the best one. The problem was the best one was Johannes Kepler, who did not believe that everything orbited the Earth. Well, what do? You need somebody good at math. So he said, here's the deal, dude. I'm hiring you to do this job. Look at my life's work and explain this so that it fits with my idea. Like the worst thing you can do in science. Here's my observations, make them fit with what I think. Not, here are my observations, let's come up with an explanation for why. Make them fit, okay? High square peg, neat round hole, right? Like it's just not going to work. That's not how you do science. Anyway, Kepler needed work. Got to put food on the table, so he's like, okay, sure. It didn't take him very long to realize this was going to be impossible if he was trying to prove Bray right. Took no time at all to prove exactly what he thought. Okay? This could only be caused by one thing. The fact that both Mars and the Earth orbit the sun. So here's Earth and here's Mars. As Earth and Mars orbit the sun, because Mars is further away, Earth will pass it in its orbit. And because they're close enough together, okay, we can observe a bit of strange relative motion with Mars. We don't notice it with Jupiter and Saturn because they're too far away. Okay? But with Mars, it's just like when you pass a car on the highway. So if I see a car way out in the distance and I'm going faster than it is, it still looks like it's moving forwards as I come up on it. But just as I pass it, if I look over to the side, what does it look like that car is doing as I pass it? It looks like it's moving backwards relative to me because we're very close now. Okay? And I have a different reference point than I had when it was way in front of me. So now, as I'm passing it, it looks like that car is going backwards. It's obviously not. It's still going forwards. But from my point of view, relative motion, it is going backwards. And then when it gets far enough behind me again, I don't really notice that anymore. And it looks like we're both going forwards. It's still falling away, but it still looks like it's moving forwards. So this is exactly what happened. As Earth passed Mars, it looked like Mars would move backwards because Earth would pass it. And then once Earth got far enough ahead, it looked like Mars was following it again. Okay? That couldn't be explained if Earth was at the center of the universe, but it worked perfectly for Earth and Mars orbiting the sun. So Kepler kind of puts Bray off for as long as possible. And finally Bray's like, what the hell am I paying you for? Like, come on, where are your results? And Kepler's like, well, I have the results, but you're not going to like it. Your results, which are meticulous and thorough, do not support your hypothesis. The Earth is not at the center of the universe. Your results clearly show that Earth orbits the sun, and so does Mars, and so does everything else. And thanks to all of your life's work, we can prove that. And Bray's like, are you kidding me? You're fired! That's not what I hired you to do. Of course, Kepler's not very happy with that. He didn't like getting fired. He was really good at math. He was really good at his job. Problem was he didn't prove Bray right. He didn't like that. So it's like a wrongful dismissal, except there wasn't like courts and lawsuits back then. So what Kepler did is what, well, probably any one of us would think about doing. Maybe some of us would do. It's not the right thing to do, but it's what he did. Revenge. He took Bray's life's work and made him a mockery. Hey, this guy thinks everything orbits the sun, but look, all of his data says otherwise. And I can prove it. Okay? It was like the single largest insult you could possibly give to someone in the scientific community. Your life's work has proven you wrong. So Bray went to his grave believing that the Earth was the center of the universe, and with his life's work proving him wrong. Would have been easier to just go, gee, I did a great job collecting all that data. I'm so awesome and the Earth orbits the sun. But no. It's that whole pride thing. Okay? Really messed with him. So anyway, that's the history of Kepler and Bray. So like one of the biggest, like Hatfields and the McCoys or Montagues and Capulets kind of thing, okay? They really butted heads. So what Kepler found about Bray's data was that it said not only does everything orbit the sun, but the orbits aren't perfectly circular. Okay? Bray's data was so meticulous and so thorough that it actually recorded that some planets, actually all of them, moved faster at some points in their orbit than others. And if an orbit is a perfect circle, that's not possible. Because if something is moving a perfectly uniform circular motion, its velocity shouldn't change, or its speed, sorry, shouldn't change. Agreed? So the only way to explain that some of the planets go faster at some of the, well, all of the planets move faster at some points in orbit than others, is that their orbits aren't circular. They're close. So what's close to a circle, but not quite a circle? An oval, yeah, or an ellipse. Okay? The ellipse was proven perfectly with Bray's data. Okay? It showed that at some points in any planet's orbit, it's a little bit closer to the sun than other points. If you get closer to the sun, that means your radius decreases. And that means you also have more centripetal force and move faster. Okay? So all of this stuff was easily explained with the data that he had on hand. Okay? And he was able to mathematically prove that this is in fact the case. Now, it's not this elliptical. Okay? This is greatly exaggerated. If Earth did this, we would consecutively fry and freeze every orbit. Okay? And that obviously doesn't happen. Okay? The Earth's orbit is almost a perfect circle, just slightly off. It's like if you took a basketball and just give it a little squeeze. Okay? That'd be about it. Okay? Most planets are like that. They're just a little bit off of a perfect circle. I don't know what I was doing with that diagram. Anyway. Okay. So, you ever notice, this bothered me. This totally bothered me as a kid. Bothered me into adulthood until I learned why it was the case. You ever notice that the seasons aren't all the same length? Or all the months aren't all the same length? That bothered me. Like, you know, because I could never remember that rhyme about, 30 days have these months, and I don't remember which months it is, and whatever. But February has 28 days. Why? Okay, it never made any sense. Never made any sense to me. Why is that much? Why can't they all just be 30? Okay, or why can't they all be whatever? Okay, and make it work. Well, the reason is because the Earth's orbit's not round. Okay? And so as a result, winter is only 89 days long. We get from one point in Earth's orbit to another in 89 days because we're closer to the sun during that time. Okay? And then as we start moving further away, okay, it starts to speed up. So autumn's only 90 days, winter's the shortest at 89, spring is 93, and awesome, northern hemisphere rocks, summer's 94. Okay, if you live in the southern hemisphere, it's reversed. And winter would be your longest. That would suck. Of course, there's no place in the southern hemisphere other than Antarctica that gets winter like us. But okay, so that's the way it goes. Okay, so and that's because Earth's getting a little bit closer to the sun at some points in its orbit than ours. Okay, meaning it moves a little bit faster and covers more of that total circle during the season of winter than it does in the season of summer when it's further away. To get an equal amount around the circle takes longer, okay, around its orbit because it's moving slower. Right? That sort of makes sense? Okay, so if you didn't know that before, now you know winter's the shortest. Okay, because obviously February is in winter, right? December 21st to March 21st. Okay, so you start late in December, which obviously has 31 days, but because you start on the 21st, it doesn't really matter. Okay, you got January, then you got February, that only has 28 days. Okay, so 30 days in January, right? 28 days in February. March 21st is the start of spring.
If it's 89 days, you said the radius is smaller. Why doesn't our Earth heat up a little, being closer to the sun?
It does ever so slightly.
Okay.
Yeah. So even though it's winter for us, winter doesn't have to do, like the seasons don't have to do with where we are in our orbit. The seasons have to do with the tilt of the Earth, right? And whether we're facing the sun or away from it. But yeah, in actual fact for us, winter happens during during perigee, one of the closest. And over time, this actually can shift. Okay, it's called a Milankovitch cycle, and it has to do with where the Earth what the Earth does with its wobble and where it is in the orbit and how it speeds up as a result of. There's a really complex relationship that can basically explain a lot of the like trends in global climate. It can also partially explain, I'm not saying that global warming is not caused by human activity. I'm not saying that there's not a relationship there, because there obviously is. But there's also other factors, and that has to do with how much time the Earth spends in summer, and how much of the northern hemisphere spends facing the sun, because most of the ice caps are in the northern hemisphere. Through this Milankovitch cycle, eventually what happens is, in another few thousand years, it'll be opposite, and we'll be tilted towards the sun when we're furthest, or when we're closest, okay, and that'll make it worse. So there's, yeah, and obviously, like right now, we're in warmer winters, which means we don't get the same snowpack, it doesn't last as long, right, and so we get, the snowpack doesn't get as thick, so it melts more quickly. We have more time where there's no snow cover. With no snow cover, there's less albedo, more sunlight gets absorbed, and it creates a feedback, right? I got a video on it, I'll show you another day. But, okay, so that's kind of what Kepler did, is he came up with this law of elliptical orbits. Okay, and then people are like, okay, that sounds nice. Can you explain it a little bit more? So he came up with this idea of the law of equal areas, which is the seasons thing. Okay, so when we're closest to the sun, we actually move through this much of our orbit in the same amount of days as we move through this much of our orbit in the summer. Okay, that sort of makes sense. That's why summer is longer. We get through this much of the orbit in 89 days, but to get through the same amount, like the same amount of the circle, takes longer over there. Okay, so the seasons are a bit different. Okay, now what we're looking at here in this chart, this is the eccentricity of each planet and other important bodies in our solar system. Eccentricity means how far off of a perfect circle are they? Okay, expressed basically as a percentage. Mercury is quite elliptical. Its orbit is quite elliptical. Almost 21% off of a perfect circle. So it's like taking a basketball and really squeezing it, okay, making it almost like a football. Not quite, somewhere in the middle. Okay, Venus has an almost perfectly circular orbit. It's less than 1% off of a perfect circle. Earth, just under 2% off of a perfect circle, so a bit elliptical. Mars, almost 10%. So it has a bit more elliptical orbit, and it's a little bit closer to Jupiter. Jupiter is very big and exerts more gravitational force, which causes its orbit to be a bit different. Ceres, which is an asteroid in the asteroid belt, 8% off. Jupiter itself, about 5% off of a perfect circle. Saturn, about the same. Okay, Uranus, by the way, that's how you pronounce it. Uranus is something else, just so you know, because lots of people pronounce that wrong. Okay, and then Neptune, okay, is almost a perfect circle, just under 1%. Pluto's crazy. It's 25%. It's also one of the reasons why it's no longer considered one of the main planets and is considered instead as a dwarf planet. Pluto's orbit doesn't look like the others. All the other 8 planets orbit in what's called the ecliptic plane. It means they can eclipse each other because they're all in line. Okay, so as they orbit and get in the way of the sun, they cause an eclipse. Pluto doesn't orbit in there. Pluto does this. Its orbit's tilted outside of the ecliptic. And its orbit is so squished that there are parts of its orbit, almost half, where it's closer to the sun than Neptune. It's not the outermost planet for about half of its orbit. Okay? So it's highly elliptical. Since it does that, it's no longer considered to be a main planet because it doesn't dominate its orbit. Okay? It goes inside of Neptune, and Neptune would dominate that orbital path. Okay? Comets and other things like them, okay, like Cygna here, which is another Kuiper belt object like Pluto, okay, like a comet, they do this. They come in really close to the sun, cross all the planets' orbits, which can be bad if they happen to be in the same place at the same time. Okay, and then they go way back out into the Kuiper belt, or even the Oort cloud, which is beyond that. Okay, way, way out, and then they slowly come back again over, hundreds of years usually. All right, now, here was the last thing, oh, sorry, this was the difference in the Earth's speed, okay? Almost 4,000 kilometers an hour difference between perigee and apogee. Now, here was the thing that Kepler found out, especially using Bray's data, that was the death blow for the terracentric universe. He took Tycho Bray's data, and he found this calculation. If he took the square of a planet's orbital period, so how long it takes to go around the sun once, and divided it by the cube of that planet's orbital radius, he got the same number for every planet. And, to add insult to injury, called it the Kepler Constant. Okay? Anything that orbits the sun has the exact same Kepler constant. Okay? That's the mathematical proof. Everything orbits the sun. That couldn't possibly happen by accident. Okay? So if we take Jupiter's orbital period squared and divide it by Jupiter's orbital radius cubed, we'll get a number, whatever it is. Okay? If we do that with Earth's numbers, exactly the same number. Okay? Works for anything orbiting the same central point. So if we do that with all of Jupiter's moons, they all have the same number because they all orbit Jupiter. Okay? So definitely the killer blow for the terracentric universe. Tomorrow, you're going to have a quiz. And then we're going to talk about gravitation, starting with Cavendish and using it. Okay?